In the previous video, we talked about stability, where stability is in terms of a state, whether is it stable or unstable, straight away. Alright, while robustness is the measurement of stability, how much can you go before you go to unstable. That's the meaning, just that meaning. Alright, so in this video we'll talk about robustness and how do we do that. But before I go into details on how do I do that, I'll just go into details on stability margins, alright, on to describe robustness. Alright, but I'll not go into this definition yet, but just to show you what is robustness in terms of systems. If then we have a single input, single output, meaning sum transfer function, open loop. Okay, or maybe closed loop lah. In another case, you have one input, one output, still the same. Okay, and that the nyquist plot is -1 over here, correct? And if you have something that is over here, this is some nyquist plot. Okay, I mean this direction. If you so for example, I'll take back this one. I'll say that single input, single output is simply open loop transfer function. If I were to close the loop now, if I were to close the loop and run the analysis, alright, this is the nyquist plot, alright. And if I were to adjust whatever thing that is configured over here, maybe I add in a new transfer function, or maybe add in two more, I actually may move the nyquist plot, may actually move and encircle the -1. Alright, so if the nyquist plot is changed, or meaning disturbed by other systems, it crosses the -1, then this means unstable. So is robustness is how much you can tank before, or how much you can tank the disturbance or whatever perturbed. Alright, then you will become unstable. That's the meaning of that. And over here he say that if the closed loop system is stable but the nyquist plot of L passes close to -1, so if I have something like this very near to -1, okay, then the system is near unstable because it's almost towards unstable. Alright, which, and in other words, we have a large lambda, and this is 1 over lambda. This means that the gain margin is very small, so we are actually going to be very unstable. Alright, and we have very oscillatory response. This means that you're going to be very responsive, or maybe, but still somewhere constant at some certain gain. Alright, and this system may become unstable with certain disturbance. So because if you close the loop, as I say G, and then if you close the loop, if you may have another disturbance that apply into this H over here, then you may actually move this nyquist plot over here, and you may actually encircle -1. Alright, and you become unstable by small perturbations, and the system is therefore not robust. Alright, and the robusticity is depends on how much you are before you go to -1. So how much you are from stability. That is just the meaning of robustness, that what I have told you earlier in the analogy of the person and person, right? The analogy of this one. Okay, and therefore let's continue. And since we know that robustness is simply the measurement of stability, then stability margin is simply to help us define the measurement. Alright, and this is why it comes back to the gain margin and phase margin we have talked about in the previous videos. Alright, and we talk about the vector margin. Alright, but in the previous video we didn't actually explicitly define much of vector margin because there is a few types of a vector margin. Alright, maybe I think 2 types, I think, but anyway, so it's just the distance the state before you become unstable. Is just robustness. Robustness is simply this meaning of that. Alright, and just to let you know that gain margin high, phase margin high, good. If vector margin high, not good. Alright, this is just something that you need to know. Okay, now an example is shown over here in order to show you what is gain margin and phase margin. And then we have a vector margin, or this vector margin is, if you don't ring a bell, is simply the what's we call the sensitivity function S. Alright, and therefore gain margin is equals to 1 over lambda. Lambda is simply the distance from the Nyquist plot to the origin. In this case, it's totally cannot see, right? So therefore 1 divided by 0 equals to infinity. So it's very good because gain margin is high. Alright, it's the distance between here. So this distance is very big. So you're actually far away from instability. This means that you are very stable. That's the meaning of that. Phase margin now is equals to minus 180 degree plus theta. Okay, what this means is that now the phase margin over here, this is the point where the Nyquist plot cross the negative, the 1 radius, right? This is you can say that it's negative L lah, okay? Because CP is equals to CP plus 1 is equals to 0. CP is equals to negative 1, L is equals to negative 1, and therefore, okay, never mind. And this is negative L, or something somewhere there. Okay. Anyway, never mind. Let's come back here. Okay. From here to the origin. All right. This is simply theta, right? This angle is theta. So minus 180 degrees plus theta. So I think theta is about 90 degrees lah. Okay. So we have minus 90 degrees. So we have approximately this amount of phase margin before we go to instability. So therefore phase margin is so very high, which is good. We are very stable. But let's take a look. The Nyquist plot over here. Alright. I draw until I don't know where am I already. But as you can see, this point over here, although the gain and phase margin are stable, but as you can see, this portion over here is very close to negative 1. Alright. And therefore this one is, if you talking about vector margin is 1 over 1 plus CP. Alright, and therefore this distance over here is 1 plus CP. Okay, so if the smaller the distance, 1 divided by 0.05, for example, you have 20. Alright, so this means that the higher your sensitivity, this means that you're more prone to how do I say, you're more prone to instability. So this is not good. I think you get what I mean, because if this distance is very small, which is 1 plus CP, 1 divided by very small, it will become very large. Alright, and therefore it's not good, because this means that you're very near to instability. And that's just the meaning of that. Sensitivity is to measure whether are you sensitive to changes or not. That's just the meaning of it. And that's why they explain this pitch over here, where gain and phase margin do not always adequately characterize the robustness. Because as you can see from the previous video, gain and phase, not previous video, previous page, is that gain and phase, if it's high, is very good, right? Because we're stable. But as for this point over here, although now I draw until very tough to see, but as for this point over here, it's very near, right? So the gain and phase margin cannot help us to solve. So we need a type of borderless margin. We call this the vector margin. And therefore we just solve for things, right? And good margins are important for performance. And good margin means that gain margin is high, phase margin high, vector margin low. That's the meaning of good margin. Okay, and this, yeah, okay. And as for this system, this gives closed loop poles, alright, close to the imaginary axis. Alright, this imaginary axis is not this imaginary axis, this is the Nyquist plot. Alright, the Nyquist contour, if you remember, is in the S domain. Okay, if you don't know anything, it's okay. It's just something to let you know, is that if you were to plot, let's say, for example, a transfer function is closed loop. Alright, G of SC, closed loop. Alright, closed loop over here. Okay, if it's a closed loop, you're gonna plot your poles and zeros over here. Right, so you have something like that. Right, but if you have not good margin, alright, and if you are more prone to all this disturbance, the next time you're gonna the next time the signal is going to change, because your closed loop is always changing, right, because of feedbacks and things like that. You may have s minus 5 now, for example, alright, instead of s plus 5. Now it's s minus 5 for one of the pole. Then you're gonna move one of this pole to this right half plane, right? So you actually move towards the imaginary axis, right? You're gonna move towards the imaginary axis, and you're gonna be very oscillatory or unstable. This is just the meaning of that. But if you don't know anything, it's okay. It's just in terms of the meaning. Alright, my fault. What fault is that? It's because I actually didn't fully understand what is vector margin. Alright, vector margin is not complementary function, which is what I've been talking all along. It is not complementary function. It's very important. The complementary function is 1 over 1 plus Cp is equals to S. Alright, vector margin is S, alright, is 1 over S is equals to Sm. Alright, so if 1 over 1 plus Cp, which this one is S, the sensitivity function, then you're just talking about C plus P. 1 plus Cp. Alright, and therefore is equals to Sm. So the margin itself is just simply the denominator of the sensitivity function. And therefore, if this value is high, alright, then, and therefore if this is high, this means that the distance, alright, the distance from where? From here, this is 1 plus Cp, correct? It's gonna increase, so you're actually very far away from the negative 1. Alright, so therefore it's a measurement of stability. Alright, so I just want to make clear that this definition for vector margin is not the one that I told you very earlier, right, a few minutes ago, or in the few videos ago. This is why I say that I suck. Anyway, so let's come back here. This is where I see this definition. This is the vector margin definition. This is the complementary vector margin. Alright, so don't mix up. Alright, this is not, vector margin is simply 1 over complementary function. Complementary vector margin is simply 1 over complementary vector what do I call complementary sensitivity function. And what am I talking? And therefore 1 over sensitivity, I just repeat again, 1 over sensitivity function is equals to vector margin. 1 over complementary sensitivity function is equals to Rm. Alright, you call this the complementary vector margin. Okay? Or in other words, 1 over this is sensitivity function, we'll have this one. This is actually vector margin. Okay, with a m subscript. Rm in this case is in fact, so this is the complementary sensitivity function, which is T. 1 over T is equals to 1 plus Cp over Cp. Right, so this thing is simply Rm. That's all. Okay? If you remember back, T is high pass. Alright? And therefore 1 over T in our case will be a low pass. This is low pass because it will allow low frequency to enter. Alright, this is the frequency log scale. Alright, so it's just a flip. Alright, so the the sensitivity function is a low pass. The vector margin, which is 1 over S, is a high pass, and same as this one. Alright, the complementary stuff is high pass, and then the complementary vector margin is a low pass, or in other words 1 over T. Okay, I hope this is pretty clear, and ta-da, this is one thing that I really understand now. And if you were to plot both of them together, this green line, alright, this green line is in fact 1 over T. alright, is a low pass, as we can see over here, alright, which is Rm lah, okay, which is equals to Rm. And then the blue line, as you know, is straight away is xm is equals to 1 over the sensitivity function. As you can see in the bode plot, alright, the gain margin, alright, the gain margin is sorry, my fault, is not gain margin, it's vector margin. Alright, the vector margin is talking about the closest, or maybe the closest I think is somewhere here, okay, it's -1. So this closest one is at the peak at this point over here for the green color. Alright, for the blue color one, or purple color I think, is the peak is the closest from the blue color nyquist plot to the -1. So it's over here, right? And therefore this one is just the phase plot. Alright, it's just the angle, from the origin. Right, or in other words, it's just the angle from the origin. How much angle, theta. Alright, things like that. Okay, I'll not go through it in details. Alright, just this is the understanding. Now, alright, comparatively, if I have a higher SM and RM, because we want our vector margin to be low and our complementary vector margin also to be low. Alright, if it's high, in this case, as you can see, alright, if this is high, or in other words, if they are very close, as you can see that this is not actually this one, it's towards -1. Zoom in, if I can zoom in more deeper, you see it's actually -1 over here. Right, the green color is nearer to -1, this blue color one is so near to -1, so their margin is actually very, very near, right? Because as the margin is very near, then this means that it's gonna peak. As you can see, they actually go into so high. Alright, their gain is actually becoming so oscillatory. It's very near already, it's very near to -1. And therefore, through this understanding, what I feel is that actually this plot, right, is actually not the SN and the RM. It's somewhat maybe 1 over 1 plus CP, which is just the sensitivity function plot and the T plot only. Okay, this is something that I really don't know lah. Okay, you know that T is equals to CP over 1 plus CP. Because this trend kind of show me that, alright, 1 plus CP, if this so-called decrease, then sensitivity function is going to increase, and therefore the response is going to be increased also. I don't know, alright, I'll leave you to think about it. This is something that's in terms of I don't know. And this is the overall summary of what I know, what I don't know, and recommendation. And definitely you know that I don't know the -L and the graph bode plot. Alright, I really don't know what the hell. Now I know that the vector margin and the stuff like that. I don't know. Anyway, I'll just paste this in the description and then you'll just watch it out. I'll see you there. Goodbye.